Okay. Welcome everyone to discussion session 4. Um, we'll solve a few questions in this discussion session. We'll also cover. I will also discuss the extension principle. Uh, I understand that it has already been taught in the lectures in the course, but we'll try to dig a little deeper into the concept because extension principle is really important from the point of view of fuzzy set theory and fuzzy logic. So we'll go a little bit deeper into the concept and we'll also solve a few problems based on the extension principle. So that is the agenda for this particular session. So, let's get to the first question. So here we have a universe X and we have three fuzzy sets A1, A2, A3 over X. And we need to identify which of the given four options are correct, right? So I hope everyone is familiar with this notation fx. It stands for the fuzzy power set of x. It is essentially the collection of all fuzzy sets over x. So in classical set theory, we have this concept of power set, right? A power set of a classical set X is the collection of all crisp subsets of X. So similar to that, we have this notion of fuzzy power set. So anyhow, we need to identify which of the following four options are correct. And we also have a clarification. UA and UB denote fuzzy union with respect to algebraic sum and bounded sum T conorm. And inverted UA and inverted UB denote fuzzy intersection with respect to algebraic product and bounded sum T norms. So in case you forgot, the algebraic sum T conorm is given like this, and bounded sum T conorm is given like this, and algebraic product T norm is given like this, and bounded sum T norm is given like this, right? So I hope you remember these expressions. I wrote them down for completeness, and we need to identify which of the four options are correct. Now, uh, solving this question would become really easy if we recall a few basic facts that has already been discussed in the previous sessions, but I just want to re-emphasize them so that I don't have to mention them again and again. And that fact is that minimum and maximum operation over real numbers are associative operations, which means that if we take minimum of b comma c and then we take the minimum of that particular quantity with a, it is same as saying that we are taking the minimum of a comma b first and then we are taking its minimum with c, right? So that's what associativity means, that instead of applying minimum operation to b and c first and then applying it with a, we can first apply it to a and b and then we can apply it to c. We can apply it with c, right? So if we were to compute the minimum of a comma b comma c, we can do it in these two particular ways. And same is the case with maximum, right? So if you pick any three numbers, any three real numbers a, b, and c, these are the two ways. These are the two associativity properties that hold. And convince yourself that this is the case. It's not very hard, right? You can actually write a proof for this, but I'm not going to do that. Convince yourself that this is the case. Also, for any real numbers a, b, and c, we also have these nice equalities. The first one says that if you add a to minimum of B and C, that is same as adding A to B and C first and then taking the minimum. And these equalities are pretty easy to prove. So I'll prove one of them and you prove the other. So we have two cases, right? B less than equal to C and B greater than equal to C. In B less than equal to C case, our LHS would be A plus minimum of B comma C. But since B is less than equal to C, this becomes A plus B. And B less than equal to C would also imply that A plus B is less than equal to A plus C. And therefore, the minimum of A plus B and A plus C would again be A plus B. So we see that LHS is equal to RHS in the case when B is less than equal to C. Similarly, in the case B strictly greater than C, LHS would be A plus C and RHS would be now B strictly greater than C would imply that A plus C is strictly greater than B plus C, and therefore the minimum of these um, two quantities would be uh, so there's a correction here. Sorry for that. Right. So the point is that you can prove these equations very easily. And similarly, you have A plus max of B comma C is max of A plus B plus A plus C. What is interesting are the last two equations, which says that when you put a minus sign in front of minimum, it becomes maximum. So A minus minimum of B comma C is maximum of A minus B and A minus C. So I'll prove the first one and you prove the other. First case is B less than equal to C, which is same as saying that minus C is less than equal to minus B. And that is same as saying that A minus C is less than equal to A minus B. So in this case, LHS would become A minus B and RHS would become A minus B, right? Because minimum of B comma C is going to be B. So LHS would be A minus B and RHS is maximum of A minus B comma A minus C. And that is clearly A minus B. And similarly, you can do the B greater than C case. So the point is that these set of equations, the associativity of minimum and associativity of maximum, and the fact that addition and subtraction behave in this particular manner with minimum and maximum is very helpful, not just for solving the previous question, but in general, because in fuzzy set theory, we do a lot of minimum and we do a lot of maximum. This is something that I believe you must have noticed. Okay, so let us see if the first option is correct. So what is the membership function of this fuzzy set? So A1, A2, A3 are three fuzzy sets. When we take their intersection with respect to bounded some T norm, it's again going to give us um, a fuzzy set. What is the membership function of that fuzzy set, right? So this is equal to, right? So you take the membership value of X in A1, A2, A3, and then you apply the bounded sum T norm. Now, since IB, or for that matter, any T norm I is associative, this is basically same as saying this, right? Now, I'm just substituting the formula of IB. Remember, the bounded sum T norm applied to alpha comma beta is maximum of 0 comma alpha plus beta minus 1. So this is maximum of 0, the first argument, plus the second argument minus 1. Now, I'll just I'll just put in the formula for IB of mu A2x and mu A3x. That is right. Now, this is basically mu A1x minus 1 plus maximum of this particular quantity. Now, from the equation that we just discussed, this would become maximum of mu A1 x minus 1 comma just a minute, 0 comma sorry for that. Let's resume. Okay, sorry for the interruption. Okay, so we were on this question, right? And we just saw that this particular quantity is basically I of B mu A1x, right? And then we simply put in the formula for IB, and that would give us maximum of 0. So just so you do not forget, IB of alpha comma beta is maximum of 0 comma alpha plus beta minus 1. So this is the bounded sum T norm. So all you need to do is just substitute in the formula, and then you apply the formula once over, right? So the first argument plus the second argument, and the second argument is this quantity, minus 1. Now, we use the fact that maximum of A plus maximum of B comma C is same as maximum of A plus B comma A plus maximum of A plus B comma A plus C. And that would give us, so here for us, A is mu A1 x minus 1. So I hope you are able to see that A is mu A1x minus 1, mu A1x from here, minus 1 from here. And then we simply slide it inside the maximum. right? So I'm going to write all the mu ai's together, and there's one, there's minus one from here, and then there's already a minus one inside the inner maximum. So this would give us two. Now we also know that maximum is associative, right? That maximum of a comma maximum of b comma c is same as maximum. You take the maximum of a comma b first, and then you take its maximum with c. So I'm going to use that fact here. Again, all you got to do is do this little manipulations, minimum, maximum, associativity, and you'll find that the question is solved, right? Now notice that mu a1x is going to stay in the unit interval, right? Because it is the membership value, therefore it will lie between 0 and 1. And therefore, when you subtract minus 1 from it, it would become less than 0, but greater than equal to minus 1. And therefore, if you take the maximum of 0, comma mu a1 x minus 1, this would be 0, right? This, on the other hand, is greater than equal to, so sorry, right? So basically, this whole thing boils down to this. While the option says that the mu a1 intersection a2 intersection a3 is equal to maximum of 0, comma mu ai's x, so summation of this mu ai minus 1, while what we derived tells us that it is not minus 1 but it is minus 2, right? So you take the maximum of 0, sum of mu a1x, mu a2, mu a2x, mu a3x, and then you subtract 2, while the option says that it is minus 1. So clearly this option is incorrect, right? And in fact, you did not need to do this entire derivation. It is very evident from the option itself that if you set all this mu a1x, mu a2x, mu a3x to some membership value closer to 1, so maybe zero point 0.8, then this whole thing would become maximum of 0, comma. So mu zero point 0.8 added to itself three times is 2.4, and 2.4 minus 1 is 1.4, and maximum of 0, comma 1.4 is 1.4. But the membership value is always a member of the unit interval. So this that automatically gave you a contradiction. So you did not need to do this entire derivation, but I just wanted to do it to show that this is how you can derive the membership function of A1 intersection A2 intersection A3, where intersection is done with respect to bounded sum T norm. Okay, so the first option is incorrect. Uh, the second option is the membership function of A1 union A2 union A3 is this particular thing. And here union is taken with respect to the bounded sum T conorm. So I will just write the formula of bounded sum T conorm. It's minimum of 1 comma alpha plus beta, right? So again, we start by using the fact that T bounded sum T conorm, or for that matter, any T conorm is associative. So UB mu a1x, mu a2x, mu a3x can be evaluated by first evaluating mu a2 and mu a3, mu a3x with respect to bounded sum T column, and then you evaluate it with respect to mu A1x, right? And then we substitute the formula. The thing to notice here is that I'm not doing anything fancy, right? All I'm doing is just taking minimum and maximum, applying the formula once again. Now we know that minimum of A plus minimum of B comma C is same as minimum of A plus B comma A plus C. So I'm going to use that fact inside it here. So I'm going to send mu A1x inside this minimum. Now I'm going to use the fact that minimum is associative. So the innermost minimum can be shifted to the first two arguments, that is 1 and 1 plus mu A1x. Right? So I'm using the fact that minimum operation is associative. So minimum of A comma minimum of B comma C is same as minimum of A comma B, and then you take its minimum with C. Now, mu A1x is a membership value, therefore it is in the unit interval. When you add 1 to it, it is in the interval 1 comma 2. And when you take the minimum of 1 with 1 plus mu A1x, you'll end up getting 1. So this whole thing evaluates to mu minimum of 1 comma mu A1x plus mu A2x plus mu A3x. So this option is correct. Moving to the next option. Now, I'm not going to do it here. It's pretty easy to see that this is correct, right? And convince yourself that this is the case, right? Use the associativity to write the membership function of A1 intersection A2 intersection A3, where intersection is done with respect to algebraic product Tino, and derive that it actually looks like this. Again, just use associativity and you'll be fine. So option C is correct. Now option D. Here we have a fuzzy union with respect to algebraic sum T column. So in case you forgot, the algebraic sum T column is given by this formula. And we need to verify if this option is correct. Now we have three mu AIs added together here. This automatically gives us a sense that if we take this mu AI x to be very close to 1, so maybe 0 0.9, 0 0.9, 0 0.9, then this whole thing will evaluate to 2.7. And what we're subtracting is 0.9 cube. So this is 0.081, if I'm not wrong. The point is that when you take this difference, you'll end up getting a value greater than 1. But membership values are supposed to belong to the unit interval. And therefore, this option is incorrect. So you can very well derive the formula for this particular fuzzy set, A1 union A2 union A3, using associativity and all that. But we just needed to identify which of the options are correct. And here it's very clear that you can produce a counter example, right? So uh, what is the exact counter example here? Uh, uh, so let's just take our universe to be a singleton set A. and our fuzzy set A1, A2, A3 to be zero point 0.9 A. And that gives us a counterexample to this option. So I hope I gave you a sense of how to approach questions like questions wherein you are taking union of more than two fuzzy sets or intersection of two fuzzy sets with respect to some t norm or t conorm. Again, let's get to the next question. We have a universe X and we have two fuzzy sets A and B over X, and we need to identify which of the following four options are correct. We are taking union with respect to maximum and algebraic sum t conorms, and we are denoting it by UM and UA, standard notation, but there was a clarification. So in case you forgot, the maximum t conorm is nothing but the maximum operation, and algebraic sum t conorm, as we just indicated, was alpha plus beta minus alpha beta. So which of the following four options are correct? So uh, let's try to approach this. Let's try to approach this problem option by option. So the first option says that the alpha cut of A union B, union here is taken with respect to algebraic T conorm, algebraic sum T conorm is a subset of alpha A union alpha B. So, right. So let us take an element. So by definition, this means this, and when we apply the formula for algebraic sum T conorm, we get this, right? Now, if this option is true, then that would mean that if X is a member of this set on the left hand side, X would also be a member of this set. So for X to belong to RHS, that is for X to belong to A union alpha A union alpha B, we need this, right? So for X to belong to union of two crisp sets, it needs to belong to at least one of them, or this needs to hold. Now, what we know is that this particular inequality holds. And for us to show that this option is correct, we must be able to show that from this, we are able to derive this, right? Now, it doesn't seem likely, right? It doesn't seem that that is the case because so, for example, if you take, and the reason why I'm having this intuition is because this is a slightly weaker condition, right? Because you are asking that uh, one of mu ax and mu bx needs to be greater than or equal to alpha. And that has to be implied from this statement, right? And this is a weaker statement. So uh, intuition tells us that this may be wrong. We are not sure, right? So we need to figure out, we need to, construct some example and see if we're able to construct an example that can, that would help us show that this condition holds, but this condition does not hold. That is to say that you are able to find a member in this set that is not a member of this set. Now, we want this condition to be not fulfilled. So what if I take an x naught such that um, 0.2, 0.3. So we want this condition to be not fulfilled. So I'll take alpha to be 0.4, for example. Now clearly 0.2 is not greater than 0.4 and 0.3 is also not greater than 0.4. So From this, we can say that X does not belongs to the zero point 0.4 cut of A union zero point 0.4 cut of B. Now let us evaluate mu A x naught plus mu B x naught minus mu A x naught times mu B x naught. So this is zero point 0.2, this is 0.3, and this is 0.2 times 0.3, which is 0.06. So we have zero point 0.5, which is 0.50 minus 0.06. So this is 0.44, which is in turn, which is greater than equal to 0.4. Thus, x naught belongs to 0.4 cut of A union B, but x naught does not belongs to the union of zero point 0.4 cut of A and B, right? So we are able to find a member that belongs to left hand side, but does not belong to right hand side. So this option is certainly not correct, right? So my approach was this. I picked an element from left hand side, the set in the left hand side. Now, if this option were to be true, that X would also have to belong to the set on the right hand side, which is alpha A union alpha B. And for that to happen, this condition must hold. Now, intuition, we are able to intuit that it is unlikely that this would hold. And we tried to construct a counter example. And this is how we did that. So again, it's about trying to figure out what seems likely and what does not seem likely, and do a little bit of shuffling. Now this is the next. This is the second option. So again, we start by picking an element on the left hand side. So if X is a member of alpha union alpha B, then either X is a member of alpha A, that is alpha cut of A, or X is a member of alpha B, that is alpha cut of B. So this much we know. Now, for this option to be true, X would have to belong to the set on the left hand side, on the right hand side, and for that to happen, we would need this to be true, or in other words, this to be true. Right? Now, if this condition holds that mu a x greater than equal to alpha or mu b x greater than equal to alpha, certainly suggests that mu a x plus mu a2x would certainly be greater than equal to alpha, right? Because one of them is going to be greater than equal to alpha. Therefore, the sum is going to be greater than equal to alpha. And then we are subtracting the product of mu a1 and mu a2. Now, these numbers are in the unit interval. So when you multiply them, you end up getting a smaller number. So therefore, it seems that this option is correct, right? Question then is how do you actually prove that? So how can one do that? So maybe it would be prudent to make cases. So we know that X is a member of alpha A union alpha B. Then that means one of these two, this condition holds. That is either mu AX is greater than equal to alpha or mu BX is greater than equal to alpha. So we can make two cases. So suppose I consider the case wherein mu AX is greater than equal to alpha. Then okay, so yes, this would work. Now note that this thing is greater than equal to alpha. This thing is a member of unit interval. This thing is a member of unit interval. So 1 minus this thing is again a member of unit interval. and we are multiplying two numbers from the unit interval. So that again would give us an element in the unit interval. So therefore, what we have here is alpha plus k, where k is some element in the unit interval, and therefore this would certainly be greater than equal to alpha. And therefore, from this, it would follow that x belongs to the alpha cut of A union B, where union is with respect to algebraic sum T colon. So we proved that this, and similarly, this case can be done. So do this on your own. So this option is correct. Let us see another option. So this is the third option. We need to find out if this containment relation, this subset relationship holds or not. So we again will take an element in the left hand side, the set on the left hand side. Now for X to be a member of the alpha cut of A union B, here union is with respect to maximum T colon. This need to hold true. Right? So I hope, okay, so maybe I'll write, I hope this is clear to you. This is mu AX comma mu BX. If the maximum of mu AX and mu BX is greater than equal to alpha, one of them has to be greater than equal to alpha, right? Because this means, and it is easy to see why that is the case, because if both of them were smaller than alpha, then that would mean their maximum would also be smaller than alpha, but that would contradict the fact that the maximum of these two quantities is greater than equal to alpha. So certainly this implies that one of mu ax or mu bx is greater than equal to alpha. No, that is same as saying that x belongs to alpha cut of A or x belongs to alpha cut of B. And that is same as saying that x belongs to alpha cut of A union alpha cut of B. So this was pretty straightforward. This option is definitely correct. Similarly, the last option, again, we take an element in the left-hand side set. This would mean this. So again, I'm not doing something fancy here. I'm just using the definitions and making simple conclusions. Now, now we know that one of these two condition holds, that it is either the case that mu ax is greater than equal to alpha or mu bx is greater than equal to alpha. So the maximum of mu, so this implies is greater than equal to alpha. If one of the numbers is greater than equal to alpha, then the maximum of those two numbers is certainly be going to greater than is certainly be going to be is going to be greater than equal to alpha. Right? I hope that is clear. And this would in turn imply, because maximum of mu ax comma mu bx is nothing but membership function of A union B, union with respect to maximum T colon, evaluated at x. And this would in turn imply, so option D is also correct, right? So option C plus option D together tells us that when you take the union with respect to the standard T colon, which is the maximum T colon, and takes its alpha cut, it is same as taking the alpha cut of A and B before, and then you take their union. So in that sense, taking maximum T colon is nice because it behaves nicely with the alpha cuts, right? So that is an inference that you can make here. Okay, so These two questions would help you with the first few questions with assignment 5. Now let us discuss something called as decomposition theorem. Now this is a topic that's going to be taught later on in the course, and therefore I won't go very deep into this. The reason why I'm discussing this topic is because here I'll discuss a concept uh, that is helpful from the point of view of assignment 5 and assignment 6. Again, you don't need to know decomposition theorem to solve those two problems, but I think it would give you a better sense of why those sets, why that particular concept is important. So suppose X is the universe and A is a fuzzy set over X. Now we know that if we pick any alpha in the unit interval, I can define an alpha cut of A, right? An alpha cut of A is essentially the set of all members of the universe that belong to A with a membership value at least alpha. And it is not difficult to see that this is essentially a crisp subset of X of the universe, right? The point is, you give me a fuzzy set A, I can compute in its alpha cuts for all alpha in the unit interval. Now, with each of this alpha cut, I can associate a fuzzy set that I'm going to denote by this. So the way we denote alpha cut is that we put A, we write A, and then we put a alpha in the superscript in the left hand side. Superscript meaning in the above. So we write A and then we put a alpha in the superscript in the left hand side. This particular fuzzy set is going to be denoted by writing A and then putting a alpha in the subscript that is at the bottom in the left hand side. So alpha cuts are crisp subsets, and with corresponding to any alpha cut, I'm going to associate a fuzzy set that I'm going to denote by this and define like this. So the membership of X to this alpha A, so I'm going to pronounce it alpha A. Alpha A, and I'm going to pronounce this as alpha cut of A, right? Just to avoid confusion, I will denote alpha cut of A, I'll pronounce alpha cut of A explicitly as alpha cut, and this set, this fuzzy set as alpha A. Now, alpha A, the membership of X in alpha A is alpha times. Notice that this is the characteristic function, right? So we know that the alpha cut of A is a crisp subset of X, right? So either an element belongs to that set or it does not belongs to the set. So therefore, which is same as saying this. And what I'm saying is that I'll simply multiply. So to define this set alpha A, I'll simply multiply the characteristic function of the alpha cut by alpha. So if you expand this, you essentially get it is alpha if mu ax is greater than equal to alpha and it is 0, right? So to summarize, given a fuzzy set A, we know how to compute the alpha cuts. Corresponding to those alpha cuts, we can define this set alpha A like this. And these fuzzy sets are very simple in the sense that they either assume the membership value alpha or they assume the membership value 0, right? So in some sense, they are similar to classical sets. Classical sets have membership value 0 or 1. But in this case, for this set, for this fuzzy sets alpha A, membership value is either alpha or it is 0. So in some sense, they are similar to classical sets, right? Now, interestingly, this fuzzy set A can be decomposed in terms of this nice sets that we just defined, alpha A. And this is how it decomposes. Start with your fuzzy set A, you extract all the alpha cuts. Corresponding to those alpha cuts, you define alpha A. And you can recover A from this sets alpha A by just taking their union. Yeah, this is basically the standard fuzzy union, right? And this is what the decomposition theorem says. And I hope that you now understand why the word decomposition is used here, because we can decompose any set A, any fuzzy set A into this sets alpha A. And those sets alpha A can be used to construct the fuzzy set A back. So that is why these fuzzy sets alpha A are worth defining, right? So if you encounter them in assignment 5 or in assignment 6, don't get too surprised. It's just not, it's not a just a theoretical concept. It has a meaning. And in fact, one way to interpret these sets, fuzzy sets alpha A, are atoms as atoms, right? Because they can be used to build the set fuzzy set A back, and they are very simple in the sense that they attain the membership value 0 or alpha. So one way to interpret this sets alpha A as being atoms of the fuzzy set A. This is not a standard term, but it is helpful to think of these sets alpha A as atoms. So I'll just take an example here. Our universe is this. Our universe is finite, 1, 2, 3, 4, and 5. And I define a fuzzy set A over my universe like this. I hope you are not, I hope you're able to recognize that this is indeed a fuzzy set A, right? So the membership value of 1 is zero point 0.2, of 2 it is zero point 0.7, and so on and so forth. Now let us compute the alpha cut. So for a moment, forget the sentences. Forget the sentence. The interesting values of alpha are 0 0.2, 0 0.7, zero point 0.3, and 1. Forget the sentence for a while. Let us just compute the some alpha cuts of A. So the 0.2 cut of A would be the set of all elements in my universe that belong to A with membership at least 0.2. Now, it turns out that 0.2 of A is the entire set X. I hope you are able to appreciate, I hope you are able to recognize this. The 0.3 cut of A is a set of all elements in X that belongs to A with membership at least 0.3, and that is 3, 4, 2, 3, 4, and 5. The 0.7 cut of A is 2, 5, and the 1 cut of A is just 5. There's a typo here, right? So I just computed some alpha cuts of A. More specifically, I computed 0.2 cut, 0.3 cut, 0.7 cut, and the 1 cut. Now, the, the thing to notice here is that these are the only interesting alpha cuts, in the sense that if you compute 0.25 alpha cut, this is same as zero point 0.3 cut of A. If you compute I don't know, 8 cut of A, it is same as 1 cut of A, right? Because since our fuzzy set A attain only 4 distinct membership values, therefore, if you pick any alpha between say 0.2 and zero point 0.3, for any alpha between 0.2 and zero point 0.3, the alpha cut of A is going to be same as zero point 0.3 cut of A. Similarly, for any alpha between say zero point 0.3 and zero point 0.7, the alpha cut of A is same as zero point 0.7 cut of A, right? So we don't need to compute all the alpha cuts. It suffices to compute these 4 alpha cuts, 0.2, 0.3, 0.7, and 1, right? And I hope you recognize this, because certainly, because now what we have done is that we have reduced our space of consideration. We no longer need to consider all these alpha cuts. It suffices to consider just 4 alpha cuts. And in that sense, the interesting values of alpha are this. So I hope this sentence makes sense to you now. Now I will just draw a diagram here So this is 1, this is 2, this is 3, this is 4, this is 5, and this is point 0.2, this is point 0.3, this is point 0.7, and maybe this is 1. So the membership value of 1 is point 0.2. So we have a point here, and I indicate that using this point. Membership value of 2 is point 0.7, so maybe we have something like this. For 3, it's point 0.3. For 4, it's point 0.3 again, and for 5, it's 1. Right? Now let us uh, indicate these fuzzy sets on this diagram. Recall, this is, in other words, it's point 0.2 if x belongs to point 0.2 cutoff A, else it is 0. Okay. And suppose I use the symbol triangle for this. Now, since point 0.2 cutoff A is the entire x, this is equal to point 0.2 for every x, for every element x. So now let us use star symbol for point 0.3 A. Now, since point 0.3 cut is 2, 3, 4, 5, we'll have something like this. Let us now show 0.7a and say I use the symbol square. Now the 0.7 cutoff is just 2 and 5. And let us finally denote the 1 cutoff and say I use this inverted triangle. Now since the 1 cutoff just consists of 5, you'll have this. So what I have done here is I computed the interesting alpha cuts of A, and then I denoted graphically the corresponding alpha A sets, alpha A fuzzy sets. And this is how they look like. Now, if you take the maximum of all these sets, so if you take the union, now notice that we are using the standard fuzzy union, and that is same as maximum. So if you take the union of this alpha A set, alpha A fuzzy set, you'll get back your fuzzy set back. And that is easy to see here because if you take the evaluate this union at x equals to 1, that is same as, so you just need to consider this particular membership value 0.2. You'll end up getting 0.2. If you evaluate it at x equals to 2, you need to consider these three membership values. And we are taking the maximum. So the maximum is this one here. So you get 0.7. At x equals to 3, you have these two membership value. The maximum one of them is 0.3. At x equals to 4, you do the same thing. This maximum fuzzy set evaluated at x equals to 4 gives you 0.3. And similarly at 5, you end up getting 1. And it is obvious, and it then becomes clear that this union is nothing but the fuzzy set A. So uh, you'll be taught this decomposition theorem in detail in the coming lectures. But all I wanted to establish in this slide was that this particular fuzzy set alpha A is worth defining. Okay. Now we have a question. We have two fuzzy numbers, A and B. So A is a triangular fuzzy number and B is a trapezoidal fuzzy number. And C is the union of A and B with the standard fuzzy union, so the maximum T norm. So in other words, the membership function of C would look like this. And then we need to identify which of the following four options are correct. So for alpha between 0 and 1/3, mu alpha C of x is equals to alpha if and only if x belongs to this range. And similarly, we have three other options. So it is a good idea to just a minute. So it's a good idea to start by drawing the membership function of these two fuzzy sets. So this is A and this is B, right? So the parameters, so at 0, A attains the membership value 1, and from -2 to 0, the membership value increases, and from 0 to 2, membership value decreases, and everywhere else it is 0. So this is A and this is B. Now, how will C look like? C is the union of A and B, the standard fuzzy union. That is, you are just taking the maximum to obtain the membership function of C. You just need to take the maximum of membership function of A and B, as I just indicated. So that means in order to obtain the graph of the membership function of C, all you need to do is look at this green graph and purple graph and take their maximum or take the upper envelope. In other words, this would be the membership function of C. I hope that is clear to you. I have already discussed this in the previous session, but I just repeated that for emphasis. In other words, this is this is our fuzzy set C, the graph of the membership function of fuzzy set C, right? Now, uh, it is so let us try to write down the equation of the membership function of C. So this is the graph, and from the graph we can easily figure out the equation. So this is 0 and this is -2. So the equation of this line would be x plus 2 by 2. Similarly, this is 0, and notice that this particular portion is coming from this line, the line that joins 0 comma 1 to 2 comma 0, right? Therefore, this is nothing but 2 minus x. Similarly, this line joins 3 comma 1 to 4 comma 0. So it's 4 minus x. And this line is coming from the line joining 2 comma 1 to 1 comma 0. So this is x minus 1. And what is this intersection point P? So that can be computed by figuring out that the intersection point of these two lines. Is the equation correct? Okay, sorry. So this is 2 minus x by 2, right? Because this line joins 0, comma 1 with 2, comma 0. So this is 2 minus x by 2. Sorry, my bad. So the point is that you can easily write the equation for the membership function of C by looking at the graph. All you need to figure out is the lines, the equation of these straight lines. And I hope you know how to do that, right? It's a part of 11th class math curriculum. So this point P is 4 by 3, comma 1 by 3. And the equation of C looks like this. So it is 0 if x is less than equal to minus 2, right? Because left to minus 2 it is 0 and right to 4 it is 0. Between minus 2 and 0 it is x plus 2 by 2. From 0 to 4 by 3 it is 2 minus x by 2. From 4 by 3 to 2 it is x minus 1. Between 2 and 3 it is 1. Between 3 and 4 it is 4 minus x. And after 4 it is 0. And that was already accounted for in the first piece of definition. So this is basically the equation of the membership function of C. Now, what we are interested is in the alpha cut of this membership, if this set fuzzy set C, right? Because the options involve alpha C, and alpha C is the fuzzy set corresponding to the alpha cut of C, right? So we need to figure out the alpha cut of C. So this is how our C looked like, and this is how our fuzzy set C looks like, and this is the equation of the membership function. Now let us try to find the alpha cut. So let alpha to be a number in the interval 0, 1 excluding 0, because 0 cut of any set of any fuzzy set C would anyway be the entire real line, right? So I hope this is clear to you. So we are only interested in the non-trivial alpha cuts, so to speak. So alpha is greater than 0. Now, if this alpha, and recall this point P was 4 by 3, comma 1 by 3. Now, if this alpha is greater than 0 and less than equal to 1 by 3, that is something like the blue line, and this blue line can be made to move a little bit in the upward direction. So as long as this y equals to alpha, we have a y equals to alpha where alpha is less than equal to 1 by 3. The alpha cut would essentially be the interval L alpha, R alpha, right? I hope that is clear to you. How do we find the alpha cut of a fuzzy set? You draw the membership function, and then you draw the line y equals to alpha. You look at the intersection points, and that gives you the alpha cut, right? For any x between L alpha, sorry, and R alpha, the membership function of C evaluated at x is going to give you a value greater than equal to alpha. So for example, if I pick x here, you'll get the membership function C, and that is certainly greater than alpha. So I hope that is clear to you, right? I'm belaboring this point. I have already discussed this in the last discussion session, but I just wanted to re-emphasize how we find alpha cuts. I'm sure that it is obvious to you, but I just thought it would be a good idea to repeat it. This point P, comma 1 by 3. So the alpha cut of C would be this point, and recall the equation of this line was x plus 2 by 2, and the equation of this line was 4 minus x. So to obtain L alpha, you just need to set x by 2 equals 2. And to obtain R alpha, you need to set, right? So L alpha is nothing. The x coordinate of L alpha is this particular point is 2 alpha minus 2, and this is 4 minus alpha. So therefore, your alpha cut becomes this. And therefore, now recall alpha C is a fuzzy subset of real line, and its membership function looks like this. It is alpha when x belongs to the alpha cut of C, and it is 0 otherwise. So therefore, for alpha between 0 and 1 by 3, if and only if x belongs to the alpha cut of C, if and only if x belongs to 2 minus alpha, 4 minus alpha, right? Again, nothing fancy. You compute the alpha cut, and that can be done just by looking at the graph of membership function of C. And from there, you can write the membership function of the corresponding alpha C. Now, what if your alpha is greater than 1 by 3? Then in this case, your alpha cut is actually a union of two intervals. So for if you take alpha to be say 0.5, it is clear that it intersects the membership function of C at 2 points. So maybe this is L alpha, R alpha, L alpha dash, R alpha dash. So the union, the alpha cut of C in this case would be the x coordinate of L alpha union right? Because if you pick any x between L alpha or L alpha and R alpha, so maybe somewhere here, the membership value is going to be greater than 0.5. And if you pick any x here as well, you'll get a membership value greater than 0.5. So the point is that for alpha greater than 1 by 3, you have a alpha cut looking like this. So we just need to find the L alpha, R alpha, and L dash alpha and R dash alpha, right? I'll just erase that. Recall the equation of this line is x plus 2 by 2. This is 2 minus x by 2. This is x minus 1, and this is 4 minus x. So to solve for L alpha, we'll simply put x by 2 equals to 2 alpha, and that would give us 2 alpha minus 2. So to solve for R alpha, we'll put 2 minus x by 2 equal to alpha, and that would give us, to solve for L alpha dash will put x minus 1 equals to alpha, and that would give us alpha as plus 1. And to solve for this, we'll set 4 minus x equals to alpha, and that would give us 4 minus alpha. So therefore, alpha c in this case would be 2 minus 2 alpha 2 times alpha minus 2 comma 2 minus 2 times alpha union alpha plus 1 comma 4 minus 1. Now again, alpha c is a fuzzy set over R, and the membership function of alpha c looks like this. So it is alpha. If x belongs to alpha cut of C, it is 0 else. Thus, x belongs to alpha cut of C if and only if x belongs to union. Again, nothing fancy, just using the definitions. So therefore, this option is correct, this option is correct, and these two options are wrong. Now, we will now move to extension principle, and we'll solve a couple of problems on that. And extension principle is one of the most important concepts in fuzzy set theory. But to be able to understand it in uh, in a holistic manner, you need to have some idea about supremum and infimums. And so I'm going to go through these concepts one by one. I won't be very deep, but I'll cover I'll cover the prerequisites that are needed to understand extension principle, right? So first of all, observe that fuzzy sets take values, take membership values in the unit interval, the closed and bounded interval 0, 1. So our numerical space is the set 0, 1. All the numbers that we are dealing with come from this set. All the membership values that we are dealing with come from this set 0, 1. Now this 0, 1 is mathematically rich. It has a lot of interesting mathematical structure on it. More particularly, this set 0, 1 comes with a order less than equal to the usual order on real line, right? We know that 2 is less than equal to 3, 0.1 is less than equal to less than equal to 0.7, and so on. And this order is a partial order. What is a partial order is something that I'm not going to explain here. I assume that you know it. It's like a very basic concept in math. So this set unit interval comes with a partial order. And in fact, this partial order is a total order, which means that if you pick any two elements in the unit interval, you are able to compare them. This means for any AB, we can compare A and B, which is same as saying either A is less than equal to alpha or B is less than equal to alpha. The fact that we can compare any two elements in our partially ordered set is what makes it total order. So total order essentially means that you're able to compare any two elements in a partial order set. Furthermore, this unit interval is bounded also. That is, if you pick any element in the unit interval, it is bounded above by 1 and it is bounded below by 0, which is same as saying that A is less than equal to alpha and A is greater than equal to alpha. So I is bounded also. Furthermore, if you take any subset P of I, infimum of I and supremum of I exists and they exist in I only. So infimum, if you don't recall, is the least, it is the greatest lower bound, and supremum is the least upper bound. So what do I mean by that? So let us take a subset P of I. I here is nothing but the unit interval. Okay. Then let us use the symbol capital M. No, capital M is probably not the right choice. So X naught is called the supremum of M, supremum of P, sorry, if first of all X naught is an upper bound for P. Note that supremum is the least upper bound. So first of all, it needs to be an upper bound, and amongst all the upper bounds, it needs to be the least one. So X naught needs to be an upper bound for P, which is same as saying that if you pick any element of P, any element X of P, X would be less than equal to X naught. So X naught is an upper bound of P. Furthermore, for any X dash such that X dash is an upper bound of P, we have that X naught is less than equal to X dash. So let us try to unpack this definition. The first point says that X naught needs to be a upper bound of P, which means that every element of P has to be less than equal to X naught. So for every X in P, X is less than equal to X naught. The second point says that if you take any other upper bound X naught, any other upper bound X dash, that is, X dash is such a number which is greater than equal to every element in P. In other words, X dash is an upper bound of P. It would be the case that X naught would be less than equal to X dash. In other words, the upper bound X naught is less than equal to upper bound X dash. And this holds for any upper bound X dash. And therefore, X naught is the least, the smallest upper bound of P. You can similarly define the infimum. You can write down the definition of infimum. I'm not going to do that. I encourage you to do that. Same thing, except the concept of upper bound is replaced by lower bound. So therefore, this point would translate to for every x in P, x naught must be less than equal to x. That is, x naught is a lower bound of P. And similarly, you can translate this point. So the point I'm trying to make here is that our unit interval has this nice property that if you, since it is bounded, we have a nice property that if you take any subset P of the unit interval, its infimum and supremum is going to exist in P, in unit interval only. And interestingly, the supremum of empty set, so empty set is also a subset of 0, comma 1, right? And therefore we should be able to talk about its supremum and its infimum. Now, since 0, comma 1 is bounded, we can write the supremum of empty set as well as infimum of empty set. And supremum of empty set is equals to 0. And infimum of empty set is equal to 1. Now, this might sound a bit contradictory or a bit new because those of you who have studied calculus or analysis must have studied that we define the concept of infimum and supremum for non-empty subsets of the real line. But that is only when your underlying space is R, that is the real line. But here our underlying space itself is unit interval. And therefore here supremum and infimum of empty set can be defined as well. Okay. So the supremum of empty set is 0. And why that is the case? This is because any x in 0, comma 1, that is I, is an upper bound of empty set. Can you see why? Recall. This is the definition of upper bound. We say that x naught is an upper bound of P if x naught is greater than or equal to x for every element x in P. Now, empty set does not have any element. Therefore, vacuously, any x would be an upper bound. And if this is something that is bothering you, you can prove this. Suppose it is not the case that, so let us take an element x in the unit interval, and suppose x is not an upper bound of empty set. Therefore, that would mean there exists an x not in the empty set such that x is strictly greater than x naught. Right? If you are saying that x is not an upper bound of your empty set, which means that you are able to find an element in the empty set that is strictly greater than x. Only then x won't be an upper bound of empty set. But this is a contradiction because you are suggesting that x naught belongs to empty set, but empty set does not contain anything. So therefore, any element, so this might sound a bit counterintuitive, but it's sort of interesting. When your underlying space is the unit interval, you can also define supremum and infimum of empty set. So anyways, so any x in the unit interval is an upper bound of empty set. Therefore, the least upper bound of empty set is the least number in the unit interval, and that is 0. And hence supremum of empty set is 0. And you can apply the same line of reasoning to infer that infimum of empty set is 1. So this is something you need to get to your heart. Our numerical space is the set 0, 1. All our membership values come from 0, 1. 0, 1 is a mathematically rich set in the sense that it has a partial order on it, which is a total order, and it is bounded. Our set I is bounded with respect to this order because for any x in the unit interval, x is greater than or equal to 0 and x is less than or equal to 1. And for any subset P of the unit interval, you can compute its infimum and its supremum, and they are going to lie in the unit interval only. Okay. Another last property that we'll use is this. Suppose I take two subsets P and Q of unit interval so that P is a subset of Q. Then from here you can derive two things. So we know that supremum of P and supremum of Q and infimum of Q and infimum of P are going to exist, right? Because P and Q are subsets of I, and we know that infimum and supremum of any subset of I exist. So these quantities definitely exist. But in case P is a subset of Q, you can also derive a relationship between supremum of P and supremum of Q and so on. So given, so let us prove, so I'll prove this result, you prove this one. So given P is a subset of Q. Now, for any x in P, okay, so maybe not this, but this. Can we write this? We know that supremum of supremum of Q exists, and supremum of Q is the least upper bound. In particular, it is an upper bound. Therefore, if you pick any x in Q, x would be less than or equal to supremum of Q. Now, this holds for any x in Q. Now, P is a subset of Q. So in particular, for any x in P, x is less than or equal to supremum of Q. True? But this means that supremum of Q is an upper bound for P. But supremum of P is the least upper bound. Therefore, supremum of P must be less than or equal to supremum of Q. And hence, we have established this result. Again, just using the definitions, nothing more. So P is a subset of Q would mean that supremum of P would be less than or equal to supremum of Q, and infimum of Q would be less than or equal to infimum of P. And it is not difficult to see why this is the case. So maybe I can take an example. So 0 point, right? So this is our P and this is our Q. Obvious that supremum of P is zero point 0.7, which is less than equal to zero point 0.8, which is the supremum of Q. So when you're taking the supremum, it becomes supremum of P is less than equal to supremum of Q. And infimum of Q is zero point 0.1, which is less than equal to zero point 0.3, and that is the infimum of P. So I hope this makes sense to you. Now, just give me a minute. I'll plug in my iPad. I'll I'll plug in my charger and then we'll continue. Okay, so continue. Now we will motivate why extension principle is needed. So we have done fuzzy arithmetic in the last week, right? Wherein we saw how to perform standard arithmetic operation on fuzzy numbers, operations such as addition, subtraction, inverse, division, and so on. Now, we did achieve this using the help of AlphaCuts, right? Given two fuzzy numbers A and B, we found out their AlphaCuts, and then we performed addition and subtraction on those AlphaCuts. And from those AlphaCuts, we recovered back the sum and difference and multiply and product and so on. Now, a natural question to ask is that if we can perform these operations, this operation of addition, subtraction, multiplication, or for that matter, any operation, logarithm or exponentiation on fuzzy numbers. We know how to perform standard arithmetic operations, but can we perform any operation on fuzzy numbers? And more broadly, can we perform these operations on any fuzzy set? So we're no longer talking about fuzzy numbers, but can we perform operations like x square, x cubed plus 1, sine x, or on fuzzy sets, right? So the answer is yes. And that is what extension principle enables us to do. So the extension principle help us extend any function to act on fuzzy sets. Or in other words, extension principle help us fuzzify any function. And it was introduced way back in 1975 by Jade, the person who introduced fuzzy sets. And it is one of the most important um concept in fuzzy set theory and fuzzy logic. So we'll we'll cover extension principle step by step. So let us start with two sets x and y. These are crisp sets, and f is a function from x to y. A function, I assume that everyone is aware of what a function is. Now f maps elements of x to elements of y. right? So for example, if x and y are real numbers, x and y are denote the real line, and f is a function that sends x to x square, then f maps 1 to 1, 2 to 4, 3 to 9, so on and so forth. So it maps elements of x to elements of y. Now, the natural question to ask is that can we make f to act on crisp subsets of x and the inverse of f on crisp subsets of y? Can we make f act on crisp subsets of x, and f inverse to crisp subsets of y? So if f is a function from x to y, then f inverse is a function from y to x. So the question that we're trying to ask here is that, okay, f sends elements of x to elements of y. How can we make f act on subsets of x and f inverse on subsets of y? And the question is that you can, it's not very difficult. This is basically what direct image and inverse images are, right? And if you have taken a course on metric spaces or topology, or this is basically taught in the very first lecture. Now, we are going to denote these extensions, the extension of f to power set of x. What do I mean by that? F sends elements of x to elements of y. We wanted f to act on crisp subsets of x, or in other words, on elements of power set of x. Any element of the power set of x is essentially a crisp subset of x. So we want f to act on power set of x, and we want it to send it to some element in power set of y. Or in other words, f sends crisp subsets of x to crisp subsets of y. And this is how we define it. So you take a crisp subset of x and you evaluate f of a by simply evaluating f at all the elements of a. It's a very obvious definition, right? You want to evaluate f of 1 comma 2. So what do? You evaluate f at 1 and f at 2, and you put them in the set. Nothing very fancy, very obvious. Similarly, you define the inverse image of P. So we pronounce it. So this is called as the direct image of A under F. This is called as the inverse image of A, B, sorry, under F. So the inverse image of B. So given a subset, crisp subset B of Y, that is an element of power set of Y, we define its inverse image like this. So you collect all the elements in X such that their function image, that is f of x, belongs to B. In other words, suppose I want to evaluate the f inverse at 1 comma 2, the set 1 comma 2. So you are going to look at all the elements of your domain, the set x, such that f of x is a member of 1 comma 2. Or in other words, f of x is 1 or f of x is 2. Right? So got to recognize that these are pretty straightforward definitions. We're doing nothing out of the box here. Right? This is a very obvious way of defining the direct image. F of some crisp subset of X is obtained by simply applying F to every element of that set and then just putting them in a collection. And this is how the inverse image of F is defined. Now, it is worth noting that to define this inverse image, you don't require F to be invertible. When we study inverse in calculus, we are explicitly told that the concept of invertibility makes sense when your function is bijective, right? When it is invertible, basically. F inverse makes sense when F is actually invertible. But here you don't need that, right? Because this definition does not require anything about the invertibility of F. F could be anything. F could be a non-invertible function. It doesn't matter. All you are saying is that to compute F inverse of B, where B is some subset, crisp subset of Y, is that you look at all the elements of your domain X such that their image is in B. That is all. This is an interesting point that you should must keep in mind. Now there are some properties of these extensions. Now, I would like to make a remark here. F is a function from X to Y, and and these are essentially extensions of F to power set of X and power set of Y. So ideally, we should have used some different notation. So maybe F cap or F inverse cap. But for convenience, we are abusing notation. We are not using a new symbol, but we are just abusing the notation, and we are saying that we won't change the symbol, right? Or we are going to be uh, lazy, so to speak. So what would be the f of empty set? It is going to be empty set only. Convince yourself that this is the case. Similarly, f inverse of empty set is going to be empty set. Again, convince yourself that this is the case. And f of x. So when you evaluate f at the entire domain x, that essentially is the range of f. Because what would be f of x? It would be fx where x belongs in the set x. But that is precisely the definition of range of a function. Similarly, f inverse of y is the whole set x. So if you compute the inverse image of your entire codomain, you'll end up getting your domain. And I'll probably go through the proof of this property. Nothing, again, very deep. You just got to follow the definition. F inverse of y is the set of all elements in the domain whose function image belongs to y. So this is certainly going to be a subset of x, right? Because we are looking at some elements of set capital X that satisfy a certain property. So this is definitely going to be a subset of X. So this much we know. We need to show that X is also a subset of f of y. But isn't this obvious? Since f is a function from X to Y, for any element X in the set capital X, f of X is going to be in Y. And therefore, X, by definition, X is a part of f inverse of Y, right? Again, this is very trivial, but it is worth emphasizing. So from here, it follows that X is a subset of f inverse of Y, and therefore f inverse of y is equals to x. Now, before moving further, I would also like to emphasize one point. In some books, you'll find that f of a is defined like this. It says that f of a is the set of all elements in the codomain such that those elements are image of some element of A. Again, f of a is the set of all elements in the codomain Y that can be expressed as f image of some element X in A. This and this definition are equivalent. I hope you are able to see that. Convince yourself that this is the case. Right? So I will do a quick example. We have two sets X and Y. These are our universes. And then we have a function from X to Y given like this. F of A equals to f of B equals to alpha, and f of C is equals to delta. Now we need to compute f of the set consisting of A comma B. Now this is f of A comma f of B. Now f of A is alpha and f of B is also alpha. So this is the singleton alpha. Similarly, what is f of singleton C? It is set consisting of f of C, and that is singleton delta. Again, nothing fancy. So what is the inverse image of alpha, beta, delta? The set consisting of alpha, beta, and gamma under F. So just so that you know how to actually pronounce these notations. So this is a inverse image of alpha, beta, gamma under F. So again, We just write the definition. It is the set of all x in the domain such that f of x is a member of, which is same as saying the set of all x in the domain such that f of x equals to alpha, or f of x equals to beta, or f of x equals to gamma. Now we know that the way f is defined, f never attains the value beta or gamma. It only attains alpha. So in this case, and that is basically a comma b, right? Because f of a and f of b is alpha, and f of c is something else. So it's just a comma b. Again, let us compute the inverse image of the set consisting of alpha and delta under f. Again, set of all elements in the domain such that f of x belongs to set this. Now, f of x equals to alpha for a and b, and f of x equals to delta for x equals to c. So this is a comma b comma c. And in fact, this is the complete set x. So I hope these four examples gave you a sense of how what exactly is happening, right? How are we computing the direct image and inverse image? Now, that was basically the basic part. Now, let us try to express the definitions that we just discussed in terms of characteristic function. So these are the definitions we discussed, right? So f extension of f to power set of x is given by this. An extension of f inverse to power set of y is given like this. Now let us try to express f a and f inverse b for some crisp subset a of x and crisp subset b of x in terms of their characteristic function. That is, we want to sort of come up with a formula for mu of f of, sorry. Okay. So this is the definition of f on power set of x. Now carefully note this. When is the characteristic function of f of a at y is equals to 1? If and only if y is a member of f of a. And when is y is member of f of a? If there exists an element in the domain x such that x belongs to a and f of x is equals to y. Again, if you recall, so we are just applying the definition. When would y would belong to f of a? If y can be expressed as image of some element of a. In other words, there exists x in the domain such that x is an element of a and f of x is equals to y. Now this is same as saying this, that there exists x, an element x in the domain x such that characteristic function of a at x is 1 and f of x is equals to y. Now this is same as saying that if you take the supremum of characteristic function of a over all x such that f of x is equals to y, it is equal to be 1. It is going to be equal to 1. Right? Because suppose, so maybe we will prove this. Suppose there exists x such that x belongs to a, which is same as saying that the characteristic function of a at x is 1, and f of x is equals to y. Then supremum of, so we are proving the forward part, so there exists x naught such that so we're taking the supremum of this set. This is going to be equal to any individual element in that set. So we are taking the supremum of characteristic function a of x, where x is varying over the that part of the domain. So maybe it would be better to write the complete notation. This is what the supremum stands for. We are taking the supremum of characteristic function a of x, where x is varying over the domain such that f of x is equal to y. Now, this supremum is definitely going to be greater than equal to a particular element. Therefore, the, it is going to be greater than equal to psi of a of x naught, and that is 1. But this supremum is always going to be less than equal to 1. Remember, our membership values come from the unit interval, and 1 is the upper bound or is the greatest element of the unit interval. Any supremum, any infimum is so. What I'm saying is this. Right? So this supremum was less than equal to 1, and we just showed that it is greater than equal to 1, and therefore it must be equal to 1. So the forward part is established. Now do backward step on your own. So the point is that characteristic function of f of a at y is equals to 1 if and only if this holds. Similarly, when is the characteristic function of f of a at y is 0? When y does not belongs to f of a, y does not belong to f of a. Now there are two possibilities. Either y is not the image of any x in the domain. That is, the set of this particular set is empty, or it is the case that y is image of some element in the domain, but that element never belongs to a. In other words, for any x in the domain such that f of x equals to y, x does not belongs to a. Writing the same statement in terms of characteristic function tells this. Either it is the case that y is not the f image of any x in the domain, or if it is the f image of some x in the domain, then that x does not belong to a. And you can show that this is equivalent to this. Do this on your own. Nothing very hard. Just convince yourself that this is the case. Now, to summarize, this was the definition that we started with, that we defined, obvious definition. And from there, we showed that that is same as this definition in terms of characteristic function. Similarly, the definition of F inverse on the power set of phi was this, and in terms of characteristic function, it is like and let us now derive this definition in terms of characteristic function. So let us so first of all pick a crisp subset of y. Now we are interested in finding out the characteristic function of f inverse of b, right? Now f inverse of b is an element of power set of x, or in other words, a crisp subset of x. Now, and therefore, this essentially is a map from x to unit interval. Again, I'm just writing everything down. I hope you have enough mathematical maturity to follow, to like write all these things on your own. I just being a bit complete here, just so that even if you're not, even if you are not able to, you did not follow the previous part, you're able to follow this part, right? So pick a crisp subset B of Y, then F inverse of B is a crisp subset of X, and therefore its characteristic function would be from X to the set 0, 1. Now let us pick an X and carefully note that when is the characteristic function of F inverse of B at X is 1? When X belongs to F inverse of B, right? I hope everyone knows that characteristic function of M at X is 1 if and only if X belongs to M and it is 0 otherwise. Just using that idea here. Characteristic function of F inverse of B at X is 1 if and only if X is a member of F inverse of B. But by definition, that is same as saying that f of X is a member of B, or in other words, the characteristic function of B at f of X is 1. Very simple. Similarly, when is the characteristic function of f inverse B at X is 0? When X does not belong to f inverse of B, which is same as saying that f of X is not a member of B, or in other words, the characteristic function at B, the characteristic function of B f of X is 0. So in other words, this definition of f inverse on power set of Y can be written equivalently in characteristic function like this. Okay. So to summarize, we started with a function f from X to Y. X and Y are our universe. F maps elements of X to elements of Y. We said we want to make F act on subsets of X, crisp subsets of X. And we want F inverse, which is a map from Y to X, to crisp subsets of Y. And we gave the definitions in terms of direct image and inverse image. Then we derived those definitions in terms of characteristic function, and they look like this. Okay. And this is basically the basis for the extension principle. For this is basically this serves as the inspiration for defining f on fuzzy sets, fuzzy subsets of X and fuzzy subsets of Y. So we know how to extend f to power set of X, and we know how to extend f inverse to power set of Y. And by looking at this definition, we know how to extend f to fuzzy power set of X and f inverse to fuzzy power set of Y. And this is basically the basis. This serves as the inspiration. So from looking at the definition, it makes sense to replace characteristic function by membership function. So if A was a fuzzy set over X instead of just being a crisp subset, then it makes sense to define f of A to be a fuzzy set over Y given like this. So all we are doing here is fuzzifying these definitions. Wherever you see characteristic equation, a characteristic function, you replace it with membership function. So you're fuzzifying the classical definitions, so to speak. Okay. So the above definitions serve as inspiration for extending f to fuzzy subsets of X and f inverse to fuzzy subsets of Y. So we basically replace the characteristic function psi with the membership function mu when we extend f and f inverse to fuzzy sets. And this is basically what the extension principle is. Extension principle is the following. F is a function from X to Y. X and Y are our universe, crisp sets. Then F can be made to act on fuzzy subsets of X in the following manner. So if you give me A, I apply F on it, and I get F of A, which is a fuzzy set over Y. And this is how it is defined. You take the supremum of mu A of X where x is varying over your domain x such that f of x is equal to y. Similarly, if you give me a fuzzy subset B of y, I apply F inverse on it, and I get a fuzzy subset over X, and this is how I define that set. To summarize, extension principle help us fuzzify functions. And if you think about it, functions are the basis of almost all of math. In different areas of math, we study different types of functions. In topology, we study, uh, continuous functions. In measure theory, we study some specific type of functions. So all of mathematics, in some sense, is the study of all different kind of functions. An extension principle enable us to fuzzify any function. If you give me any function from crisp set to crisp set, I can use extension principle to fuzzify it. And after doing that, F would be able to act on fuzzy subsets of X and fuzzy subsets of Y. So therefore, extension principle is a way to fuzzify mathematics, if I can say that. And this is how, and this is basically the definition. Okay. Now let us do a example. Uh, we have universals x and y, same as before. F is a function from x to y, same as before. F of a is same as f of t, which in turn is equal to alpha, and f of c is equal to delta. And we have two sets, a and b, two fuzzy sets. A is a fuzzy set over x, and b is a fuzzy set over y. Now we want to compute f of a. A is a fuzzy set over x. When we apply f to a, we get a fuzzy set over y. And how do we define the membership function f of a? By the extension principle. And what the extension principle says, that the membership of f of a, membership of y in f of a, the fuzzy set f of a, is supremum of mu a of x, where x is varying in your domain such that f of x is equals to y. Okay, this is through extension principle. Now, let us evaluate this membership function. So our y has 4 elements. So let us first evaluate the membership of alpha in f of a. Now, let us look at this set. Which elements of the domain are mapped to alpha? Precisely a comma b. So we are essentially taking the supremum of mu a of x, where x varies in this set a comma b. Or in other words, supremum of mu a of a and mu a of b. And this is same as maximum, right? So supremum of mu a of 1 is 0.2 and mu a of b is 0.3. So this is 0.3. Similarly, mu membership of beta in fuzzy set f of a is supremum of mu a of x, where x is varying over the domain x such that f of x is equals to beta. Now let us look at this set. Let us look at all the elements in the domain that are mapped to beta. But that is the empty set. No element of the domain is mapped to beta, because this is the definition of f. So this is same as taking the supremum of empty set, and that is 0. Similarly, what is the membership of gamma in the fuzzy set f of a? We notice that no element. So let us look at all the elements in the domain that are mapped to gamma, but no such element exists. Therefore, this is empty set, and therefore mu f of a of gamma is supremum of empty set, which is 0. And finally, we compute the membership of delta in f of a, which is the supremum of mu a of x, where x varies in the domain such that f of x is equals to delta. Now we note that only one element in the domain is mapped to delta, and that is precisely C. So this becomes supremum of a singleton set, basically mu A of C. And that is same as mu A of C, and that is 1. Okay. So I hope you got a sense of what we are doing here. Now let us compute f of b. Now b is a fuzzy subset of y. When I apply f inverse to it, I get a fuzzy subset of x. And how do I write the membership function of that set? By extension principle. And this is the definition. The membership value of x in f inverse of b is obtained by applying the membership function of b at f of x. Now let us compute the membership function of mu b. So we have three elements in our set. So in our set x, by extension principle, f of a is alpha, f of beta is also alpha, and f of c is delta. Now, what is the membership of alpha in B? It's 0.3. So therefore, we get this. So therefore, this is how our fuzzy set F inverse B looks like. Now let us do a more involved example. We have a fuzzy set over the real line given by this membership function. So let us plot this membership function. So e to the power minus x looks like this, and e to the power x looks like this. When we are taking the minimum, we end up getting this. And by the way, this point is 0, comma 1, right? Because at x equals to 0, e to the 0 is 1, and e to the power minus x is also 1, right? And we are taking the minimum, we are taking the lower envelope. So this is our fuzzy set A. So it is a good idea to expand this minimum. So it is e to the power minus x if x is greater than equal to 0, and it is e to the power x if x is less than 0. So this is our membership function A. And we want to compute f of A. Again, A is a fuzzy subset of real numbers. When we apply f to it, we get again a fuzzy subset of real numbers because f is a function from R to R. And this fuzzy subset f of A is given by the extension principle, which is given like this. Okay. So we need to find the membership function of f of A. And by extension principle, we know that this is the formula. So the membership of y in f of A is obtained by taking the supremum of mu A of x, where x is varying over the domain, which in this case is the real numbers, such that f of x is equals to y. Now, since f of x is this particular quantity, which means what we are saying is this. right? Now, notice mod x is always greater than equal to 0. Therefore, 1 plus mod x is always going to be greater than equal to 1. Now, log is a natural, is an increasing function, so you can apply log on both sides. And that would give you that log of 1 plus mod x, which is your function f of x, is always going to be greater than equal to 0. So therefore, if you pick y less than 0, then the set of all real numbers such that f of x is equals to y is going to be empty. And in this case, mu of f of a at y is essentially the supremum of empty set, and therefore it is equals to 0. Therefore, the interesting case is this, when y is greater than equal to 0. Because in this case, right? Now, we can take exponential on both sides of this equation, and that would give us this. In other words, mod of x is equals to e to the y minus 1, and therefore x is either equal to e to the power minus 1 or 1 minus e to the power y. Okay, so in the second case, when y is greater than equal to 0, the set of all x such that f of x is equals to y is e to the power minus 1 and 1 minus e to the power y. And therefore, the membership function f of a, the membership function of f of a at y is okay. Now, y is greater than equal to 0. What does that mean? It means that e to the power is greater than equal to e to the 0, which is 1. And therefore, e to the power minus y is greater than equal to 0. And this also means that 1 minus e to the power y is less than equals to 0, which means that when we apply a, therefore the membership function of a at e to the power y minus 1 is going to be this, because we know the membership function of a looks like this. When the argument x is greater than equal to 0, it is e to the power minus argument. And when the argument x is less than 0, it is e to the power argument. In this case, the argument is greater than equal to 0. Therefore, this becomes, in this case, the argument is less than 0. So it becomes e to the power argument. So in either case, sorry for the interruption. We showed that this f of a is a power set of real numbers, and it is given by this. And we proved that, right? Okay. So moving on to the next question, next aspect of the extension principle, that we know how to extend functions of the form f of x to y to act on fuzzy subsets of x and f inverse on fuzzy subsets of y. We just saw that how to do that. But most operations, most interesting functions actually have domains that are made up of two or more sets. So for example, addition operation is a function from R cross R to R, right? So you take two numbers and then you add them. Similarly, for minimum, you take two real numbers and you take their minimum, you end up getting another real number, and so on, right? So most interesting operations actually have a domain that is made up of Cartesian product of two or more sets. Now the question is this: suppose I have universe x, y, and z, and I have a function f from x cross y to z. How do we compute f of a comma b, where a is some fuzzy subset of over x and b is some fuzzy subset over y? Now, if I give you an element x and y from set capital X and capital Y, then we know that f of x comma y can be computed. But how do I compute f of a comma b when a is a fuzzy subset of over x and b is a fuzzy subset over y? So what we have is this. For a moment, call M to be x cross y. M is again a set. So f is nothing but a function from M to Z. Now, if you give me a fuzzy subset over M, then I know so f is a function from x cross y to z. If we set m to be x cross y, then f is a function from m to z. Now, if you give me a function a, if you give me a fuzzy set a over m, then I know how to compute f of a. I can simply use the extension principle, right? And what would be the membership function of f of a? It would be for every element, sorry. So f of a, so a is fuzzy set over m. We apply f to it and we get a fuzzy subset over z. And this is how the membership function would look like, right? But what we have here is not a fuzzy subset M over X cross Y. We are starting with fuzzy subset A over X and fuzzy subset B over Y. If we had a fuzzy subset over X cross Y, then we know that F of that fuzzy set can be easily computed directly using the extension principle. But what we have here is a fuzzy subset A over X and fuzzy subset B over Y. Now, it is obvious that we need to construct from this fuzzy set A and fuzzy set B some fuzzy set over X cross Y, right? Because once we do that, we can then use the extension principle and easily compute our function. The question is, how do we do that? And that is where the notion of Cartesian product of fuzzy sets come into picture. Now, let X and Y be two universes. Now, we know that X cross Y is this set. The Cartesian product of X and Y is this set. It's the collection of all ordered pairs X comma Y, where X comes from set X and Y comes from set Y. Now, more generally, if we have crisp subset A of X and crisp subset B of Y, then we can define A cross B like this. Nothing new here. An equivalent way of saying this is the following, that A cross B is a crisp subset of X cross. So notice that this is nothing but a subset of X cross, crisp subset of X cross Y. So A cross B is a crisp subset of X cross Y such that given A comma X and B comma Y, A in X and B in Y, A comma B belongs to A cross B if and only if A is a member of A and B is a member of B. Again, I'm not doing something new here. I'm just stating the definition in a slightly different manner. A cross B is this. We can write it in this way as well. That A cross B is a crisp subset of X cross Y such that A belongs to a given elements A of set X and B of set Y. A comma B as a pair will belong to Cartesian product of A cross B if and only if A is a subset of set A and B is a subset of set B. Now, using this as the inspiration, we can define Cartesian product of fuzzy sets. And here is how. Suppose X and Y are two universes. I take a fuzzy subset A over X and fuzzy subset B over Y. Then we define the Cartesian product of A cross B as a fuzzy set over X cross Y given by this. So notice that when A and B were crisp subsets of X and Y respectively, then A cross B could be defined like this, that A cross B is a crisp subset of X cross Y. That part is replaced by A cross B, Cartesian product of A and B is a fuzzy subset over X comma Y. And this part, which says that A comma B belongs to A cross B if and only if A is a member of B and B is a member of B, is replaced by this. So A comma B belonging to A cross B transforms into membership. So mu of X comma Y, and here mu is the membership function of A cross B. A comma B becomes mu A of A, and B belongs to set B becomes mu B of B. And here we have an AND. AND is basically conjunction. And what is the fuzzy counterpart of conjunction? It is a T-norm. What is the standard T-norm? It is the minimum. So therefore, this thing translates to this. Okay. More generally, given a T-norm I, we can define the Cartesian product of fuzzy set A and fuzzy set B with respect to I like this. So instead of taking minimum T-norm, you can take any arbitrary T-norm I. So the Cartesian product of A and B is a fuzzy subset over X cross Y given in this manner. Now this looks similar to fuzzy conjunction, right? Or fuzzy intersection. But the meaning is different here, right? So we are now in a position to answer this question: how to compute f of a comma b, where a is a fuzzy set over x and b is a fuzzy set over y. We first compute a cross b, and that would give us a fuzzy set over x cross y. Now we can now apply extension principle to compute f of a comma b. So this is basically, so if I were to summarize this, this happens by taking Cartesian product. Now f of a comma b is essentially defined to be f of a cross b. And this is basically can be evaluated using extension principle. Because A cross B is a fuzzy subset over X cross Y. So we have a fuzzy set over domain, and we know how to apply F on it. In other words, f of a comma b is a fuzzy set over Z given by f of a comma Z is where so basically this is defined as this. Therefore, applying extension principle gives us this mu of a cross b of x comma y coming from our domain, which is x cross y, such that f of x comma y is equals to Z. But we know that mu of a cross b of x comma y is same as minimum of mu a of x and mu b of y, and hence this definition. So the point I've been trying to make is that everything can be defined with a motivation, right? These definitions do not come from air. They have very well-defined motivation, right? So we knew how to if we set x cross y to be a set M, then given A to be a fuzzy subset over M, we know how to evaluate f of A. What we started with was a fuzzy set A over X and fuzzy set B over Y. And therefore we needed some way from A and B to obtain some fuzzy set over X cross Y. And that we did using condition product. Anyhow, let us do an example and get done with this session. This is basically the example. We have sets, we have universes X, Y, and Z. F is a function from X cross Y to Z, and it is defined using this table. So X cross Y, so X has 3 elements, Y has 2 elements, so X cross Y will have 6 elements. And how F acts on those 6 elements is listed on the table on the right. And we have sets A and B, and A is a fuzzy set over X and B is a fuzzy set over Y. And we need to compute F of A comma B. Now, F of A comma B is same as F of A cross B, right? And we know how to define that. And this is right. Now, let us evaluate at lambda. So Z has 2 elements, mu and lambda. I will evaluate it at lambda, you evaluate it at mu. So we first focus, so this is our group. So we look at set of all x comma y in the domain, which is mapped to lambda. We find there are 2 such members in the domain. Therefore, supremum of x comma y belonging to, in other words, Things are getting a bit messy, but I hope you are able to follow. Now, mu A of A is zero point 0.3 and mu B of beta is 1 and mu A of C is zero point 0.5 and mu B of beta again is 1. This is supremum of zero point 0.3 and zero point 0.5. In other words, zero point 0.5. So this is the definition of the membership of f of a comma b. We want to evaluate f of mu of f of a comma b at lambda. For that, we need to compute the supremum of minimum of mu a of x comma mu b of y, where x comma y is varying in the domain such that f of x comma y becomes lambda. We first identify those elements in the domain x cross y such that they are mapped to lambda. There are two such elements in the domain, a comma beta, c comma beta. Therefore, we need to conduct the supremum of minimum of mu a of x comma mu b of y such that x comma y is either a comma beta or c comma beta. That's what we did here. And it is now homework. Evaluate this on your own. Okay. So I will conduct, I'll end this discussion session here. It's already been 2 hours, I think. So again, thank you for joining and happy learning.